Let's look at a sequence of operation for a heat pump in heating mode. So this set up here. All right, same preconditions for operation as our air conditioner and our sequence in cooling, high voltage, low voltage, etc. The sequence, assuming a typical electronic or mechanical thermostat and non-communicating equipment. Thermostat has to go through the integral time delay or compressor protection. 24 volts is sent from R to Y and G on the thermostat. We need to edit this here. We should not have. 4 volts is sent from R to Y and G on the thermostat. Y sends power to the defrost circuit board. 24 volts is sent through the refrigerant low pressure switch. The low pressure switch is closed. Contactor coil is energized. Contacts closed, sending power to the outdoor fan motor and the compressor. G sends 24 volts to the indoor fan relay. Indoor fan relay coil is energized. Contacts closed, delivering power to the indoor fan blower motor. System runs in heating until temperature rises to thermostat set point. Every 30 to 90 minutes, if defrost thermostat is in the closed position, in other words, if that coil temperature reaches about 35 degrees, then system will enter the defrost cycle. Defrost control will power reversing valve and refrigerant circuit will switch to cooling mode. Defrost control will de-energize the outdoor fan motor. Defrost control will send 24 volts to W, powering the electric heat if it's equipped. Defrost cycle will continue until the defrost thermostat opens at about a 60-degree set point or until 10 minutes of time has elapsed. Unit will re-enter normal heating mode. This is for time and temperature defrost. Demand defrost for train equipment is a little different, but for now we're talking time and temperature defrost, typical defrost cycle that you'll see on most other equipment besides train. Really, the only difference on train is it tries to anticipate demand for defrost. So it'll kind of go through a learning mechanism where it decides whether or not the system needs to go into defrost. Depending on the thermostat model, after a predetermined time or deviations from set point, W will be energized from the thermostat. W will send 24 volts to the electric heater relays. Electric heat relay contacts will close. High voltage is sent through the limit switch, fusible link, and electric heater element. System runs until thermostat is satisfied. 24 volts is no longer sent through W, Y, or G from the thermostat. The electric heater relay is de-energized. The electric heater contacts open. The outdoor contactor is de-energized. The outdoor contacts open. The fan relay is de-energized if it's an auto, and the indoor fan relay contacts open. The control schematic, the typical control schematic, is going to look just like the one we looked at in cooling. Everything is exactly the same. We have heater relay contacts, normally closed and normally open. Fan relay contacts, normally closed to send power to the fan if the heaters are energized without the fan relay being energized. Transformer, fan relay, heater relay coil, fan relay coil. Same thermostat, fan auto on switch, auto off switch, heat cool switch, heat emergency heat switch, emergency heat thermostat, heating thermostat, cooling thermostat, auxiliary heat thermostat, low pressure switch, high pressure switch, defrost thermostat, defrost relay. All three of these is the defrost relay integral to the defrost board, reversing valve, outdoor contactor coil, condenser fan motor, compressor, or outdoor fan motor, compressor. So let's look at the system highlighting in normal heating without auxiliary heat first. We can see transformer sends power to the thermostat. Thermostat runs through the auto off switch. The 24 volts runs through the auto off switch, through the heat cool selector, which is in heat, through the heat emergency heat selectors, which is in regular heat, through the heating thermostat, through to the Y terminal, and through the fan auto on switch, which is placed in auto, into G. G sends power to the fan relay coil, opening this set of fan relay contacts, closing this set of fan relay contacts. Power is sent to the blower motor. L1 is constantly tied on to the other side of the blower motor. Power from Y goes to the outdoor unit, goes through the low pressure switch, high pressure switch, through the contactor coil, closing the contactor contacts. L1 goes through the contactor contacts to the compressor, goes down through the defrost relay integral to the defrost board, up to the outdoor fan motor. L2 goes to the compressor, to the capacitor, and to the outdoor fan motor. Right, heat pump control schematic highlighted in heating. Everything is the same as it was in heating without auxiliary heat. With auxiliary heat, we're going to have everything else plus this heater relay closes. Power sent through the heater relay, through the high limit switch, through the fusible link, powering our electric heater. It's the only thing that changes is we got power from W, and you can see it right here on the thermostat. Power comes out through the thermostat to W, powering our heater relay, closing this set of contacts, then powering the heater. Now, if the system enters defrost mode, then everything happens at the defrost control board. The thermostat's still going to be sending the same signals. So you're still going to see the same signals at the thermostat, essentially. You may see O energized depending on how the board's set up, whether or not that power is going to backfeed to the thermostat. But other than that, nothing changes from the thermostat or the air handler, really. What's going to happen is the system's going to enter defrost. Power is going to go through the logic of the unit. There's going to be 24 volts that's sent through the defrost thermostat back to the defrost board. That's going to power the defrost relay coil that's on a defrost relay sitting on the board. Sometimes it's one, sometimes it's two. I think generally it's two. The one that's most prominent is the one that powers the outdoor fan motor, or rather cuts power to the outdoor fan motor. But then the other one is going to send power to W so that if it wasn't calling for electric heat, it will turn on electric heat now. And the purpose for that is this system is essentially switching to cooling. So what we want to do is try and heat up the air as much as possible using the electric heat so that it doesn't make it so the air's coming out cold from the air handler. So if the system is not equipped with electric heat, if it's just a straight heat pump, no electric heat pack, they're going to notice that the system switched to cooling when this thing operates. So anyway, power sent to W to the electric heat. That powers the electric heat relay if it wasn't already powered, turning on electric heat. This set of contacts on the defrost relay is going to open. What that does is cuts off power to the outdoor fan motor. Then power is sent to the reversing valve to switch the system to cooling. That is going to power the system in cooling without the outdoor fan motor running, which is going to quickly raise the temperature of the outdoor unit, thawing any ice that has accumulated on the outdoor unit. As soon as that defrost thermostat opens, then the system will switch back to normal heating mode. If that defrost thermostat does not open within about 10 minutes, then it will terminate defrost and then switch back to heating mode. If there's an issue where the system can't thaw itself sufficiently, then the system will basically remain iced up and not operate very well in heating mode. Could be because it's extremely cold outside, although that's unlikely even in those circumstances. Generally, the issue is going to be one thing that's not shown on this picture of the board is you can set defrost to run every 30, 60, or 90 minutes, sometimes up to 120. But if the system continues to build up ice when it shouldn't, or when it's gone through defrost and defrost is operating properly, the board's operating properly, then you need to shorten the amount of time, how often it needs to run into defrost. Generally, 60 minutes is pretty good. 30 minutes isn't a horrible idea. But you kind of need to look at that on this specific piece of equipment and your operating conditions. But around here, generally, I'll set it to 60 minutes just to be safe. 30 minutes is a bit often most of the time for it to need to run. You know, if you got that thing set to every 30 minutes, then you're going to be only running heat 20 out of a 30 minutes when it's constantly getting cold. So every 60, even every 90 is probably okay. But if I see any issues, I will definitely set it to 60.